So today's lesson, we're going to learn about something called stoichiometry. It has a really weird name, but basically what it is a way to help us do calculations with reactants and products in a chemical reaction. So what are some things you need to know well before getting to this point in the course? One thing that's really important, writing chemical formulas. So if you know the name of something, make sure you can write an appropriate chemical formula. If you don't have that, this is going to be tricky because after writing proper chemical formulas in a reaction, you need to make sure it's balanced properly. So can you balance chemical equations? Some questions will come balanced, some won't. So if they're not balanced, you need to make sure you need to know how to do that. And then all of the calculations we've done so far involving mass and moles and particles, we use all of those again and then apply a little bit of new information with it. So if you already know enough about those things and are pretty comfortable, then we're just adding a little bit more to it. If you're still having some trouble with it, make sure you reach out for some help because we need to know those things going forward. So to introduce the topic, we're going to do a silly little example, and it's making a turkey sandwich from a chemical reaction recipe. So you want to make a very simple turkey sandwich. You take 2 slices of toast, 2 slices of turkey, 1 piece of lettuce, 1 tomato, and there's your very simple turkey sandwich. That's the recipe, but it's been put in the format of a chemical reaction where we've got pluses and an arrow, and anything on the left are the reactants, all the ingredients, and then the product is the actual sandwich assembled. So if I asked you the question, how many turkey slices would you need if you wanted to make 354 turkey sandwiches, how would you answer that question? How many slices would you need? So hopefully when you look at this recipe, you see that you need 2 turkey slices for every sandwich. So if you thought, well, since I need 2 slices per sandwich, that means I probably need to take 354 and multiply that by 2, which would mean you get 708 slices. So that's great, but here we need to show our work a little bit better than this. So we're going to go back to looking at our ratios and relationships to try and show our work. So in our recipe here, in our chemical reaction, we look at how many of each item we need and what it is. So we've got 2 turkey slices and we've got 1 sandwich. This is our ratio. So we could put it in a ratio or even put it right into our fraction format. So if I wanted to show on paper that I'm going to get 708 slices, what I would do is the same kind of approach we've been doing. Write down what we're trying to solve for, number of turkey slices, and then I start with the number that I'm given. So in this question, my ingredient, here is my product, 354 sandwiches. And then I'm going to multiply it by my ratio. So my ratio again, we're going to put in as a fraction. And I go back. I've got slices or sandwich. So one has to go in the numerator, one has to go in the denominator. Which one's going to go where? Again, has to do with your units. I want to get rid of sandwiches. Sandwiches is going to go in the denominator. And then on the top, I'm going to put slices because that's what I'm solving for. And that's the other half of my ratio. So mathematically, it's the same thing. When people thought, well, I need to double the number of slices compared to sandwiches, and that's what we're doing. 354 sandwiches times 2 slices per sandwich. Mathematically, we're still going to get 308 slices. And if we look at our units here, the sandwiches cancel out. So if you can do calculations like the one we just did with this simple turkey sandwich, you can essentially do a stoichiometry problem. Now, the thing that's different in chemistry, though, is obviously we're not cooking, we're not doing recipe with ingredients like this. We're using chemical compounds and we use moles. So as we go along, we'll try and make some references back to this example, but if you can do this, you've got the idea of stoichiometry. You just don't know it yet. So before we try out some more problems, let's just talk a little bit more about stoichiometry in itself. So if you hear the word stoichiometry more formally, you're studying moles, but specifically what is their relationship to chemical formulas and to balanced chemical equations. That's what stoichiometry really is. There are coefficients in your balanced equation. These are really important in stoichiometry. If you remember from just that example with the making a sandwich and the ingredients, there were numbers of each ingredient. Those are the equivalent of your balancing coefficients. They're going to help figure out what your quantities are for what you need in a reaction, how much product's produced, how much reactant you need, anything like that. Coefficients we can read a lot of different ways. We could talk about particles like we often do, atoms, molecules, formula units, or the big one here that we're going to use is moles. Before we try out an actual problem with chemical reactants, we have to review what a mole ratio is. So we actually already secretly did a mole ratio with our ingredients question with the sandwich. Our mole ratio for that problem making the sandwich was 2 slices to 1 sandwich. That was our hypothetical mole ratio. Now we only use mole ratios technically when we have chemical compounds. So when we want a mole ratio, it's a ratio between the coefficients in a balanced equation. So there's lots of different ratios you could come up with, but you use the balancing numbers. So in this example down here, we've got no number for zinc, but remember that just means there's a 1 there. So its coefficient's 1. There's a coefficient of 2 for HCl. For zinc chloride, no number, but remember it's 1. And for hydrogen, again, it's 1. Those are all the balancing coefficients. We could come up with any kind of ratios with these that we want. We could say that there's 1 mole of zinc for 2 moles of HCl. That could be one ratio. Another ratio we could have between a reactant and product. You could say 1 mole of zinc for 1 mole of zinc chloride. You could pick another 2, one reactant, one product, it doesn't matter. 2 moles of HCl to 1 mole of hydrogen. You can pick and make whatever ratios you want with any combination of reactants, products, or one of each. It'll all just depend on what the question's asking you. And we'll go over how to figure that out in the next problem. Now, we know leaving ratios like this isn't something we typically do. If we're using unit analysis to solve, what we're going to do is write it as a fraction. So if we took one of these, it doesn't matter. We'll pick this one here as an example. That ratio you could write as 1 mole of zinc for 2 moles of HCl. Or you could flip it around and say, well, 2 moles of HCl per 1 mole of zinc. Either one here would work, depending on what you need for your question. So, how are we going to do this? With problems, we're going to use something called the Stoichiometry Roadmap. Remember our mole roadmap? If you like these visual tools, this can be helpful for you to try and figure out the steps that you need. So when you're looking at this roadmap, and we'll come back to it when we start out a problem, we're trying to see, well, if I start with the mass of one compound, can I find the mass of another? There's no direct path between two masses. We have to use moles. We know between mass and moles, we can use the molar mass, right? This is molar mass, and we can find the number of moles. But what's different here is we've got two compounds. Number one is referring to one compound. Number two is referring to another compound. All of the problems you saw up to this point were with only one compound. These ones are switching between compounds. So how do we switch between them? That's where that mole ratio comes in. So don't worry if you're not quite sure how this is going to play out yet. Let's try a couple problems. We'll come back and we'll make some notes on these ones going forward. So we're going to try out three examples, all with the same chemical equation, but different questions that can be asked of you. So we have a balanced equation up here. Always check to make sure you have a proper balanced equation before you start these problems. Sometimes they tell you you need to balance it and sometimes they don't. So just make sure that it's balanced before you go on. This question says, if 9.61 moles of magnesium chloride are consumed in the reaction, how many moles of sodium chloride are produced? So let's rewrite our balanced equation, which is something I always like to do. So we've got it handy here. Make some references to it. Okay, so what do we have? We have 9.61 moles of magnesium chloride. So I'm going to write that down right underneath my compound here. So anything that lines up here belongs with that compound. We have 9.61 moles that are consumed, which means that's how much react. And we want to find out how many moles of sodium chloride are produced. So over here is sodium chloride. I want to figure out how many moles I have. So how do I do this? If we go back to our mole ratio over here and look at our mole roadmap, it'll help us figure it out. So we're starting off with moles of one compound. In that example, it was magnesium chloride, and we're trying to find moles of another compound, which is sodium chloride. So here we don't need to worry about mass because the question didn't ask us anything about mass, it was just moles. How do I go from moles of one compound to moles of another? Look at this. There's our mole ratio from our balanced equation. So if I want to go from here to here, I need my mole ratio. Now, what's my ratio going to be? Here I have 3 moles of magnesium chloride. And over here I have 6 moles of sodium chloride. That's the ratio that I need to use. So how do I set this up? Just like your sandwich question. What am I trying to solve for? Here I'm trying to find out my moles of sodium chloride. This is like saying how many turkey slices I need to find. We start with what we're given. Here it's 9.61 moles of magnesium chloride. Before it was the sandwiches. Now here we want to be careful with our units. Don't just write in 9.61. Write in specifically what it is. MgCl2, like that. Why? Well, we've got to put a whole bunch of moles in here and we're going to put our ratio in, so we have to be careful. I want to get rid of moles of magnesium chloride, and I want to end up with moles of sodium chloride. So here's my ratio, and I've got to put that now into my fraction format down here. If I've got moles of magnesium chloride in the numerator, I'm going to want to put moles of magnesium chloride in the denominator. How many do I have? I've got 3. So I put that on the bottom, and then my 6 moles of sodium chloride are going to go on the top, like that. And now when I look at my units, moles of magnesium chloride and moles of magnesium chloride cancel. And now I can go ahead and plug that in my calculator. So how it works, 9.61 times 6 and divide it by 3. You should get about 19.22 moles of sodium chloride, but we need to always round our answer. So here we need 3 significant digits, so I'm going to round to 19.2. So this is how you would use a mole ratio to calculate from one type of moles to another. But usually in chemistry we need to use masses, so most of the other problems that you'll run into will involve masses, and that's where the molar mass calculation will come into play. So let's try out another problem, adding in a few more steps. So we want to find out how many grams of magnesium phosphide is produced when 3.4 grams of sodium phosphide react. So we're going to do the same thing. Always rewrite your equation. This is very helpful because we're going to map out our steps that we need. Just like that. And what we know already from the question are two pieces of information. We have a mass of sodium phosphide, and we want to find the mass of magnesium phosphide. We don't know what that is. So how do we go from calculating the mass of magnesium phosphide from the mass of sodium phosphide? How do we do that? Well, let's jump back a couple slides, and we're going to go back to this roadmap here, and I'll get rid of those notes that we made from before. And let's put on what we've got this time. So in this question, we have the mass of sodium phosphide. That was that 3.4 grams given to us. And we want to find the mass of magnesium phosphide. We don't know what that is. If we look at the arrows, there's no arrow connecting the two masses, so we can't take that route. We have to follow the road. So our first step would be step 1. Find the number of moles of sodium phosphide using its molar mass. Once we have moles, then we introduce that new step with mole ratio. But this time the ratio is going to be between sodium phosphide and magnesium phosphide. Once we have moles of our product, the last step is converting it to mass, again using molar mass, but this time the molar mass of our product, magnesium phosphide. So this problem will involve a little bit more work because we have a few more steps to go. So when I'm learning these types of problems, what I always suggest to students is actually mapping this out on your diagram here. So what is step 1? I need to find the moles of magnesium phosphide. How am I going to do that? Well, we need my molar mass here. Then I'm going to try and find the number of moles of magnesium phosphide. And then we know that's step 2, mole ratio. Then I go to step 3. Step 3 again will involve molar mass. So to solve this particular problem, we need to do 3 steps to get there. So let's go through and walk through this one together, one step at a time. So step 1, I need to find the moles of sodium phosphide from the mass. You can do this step if you know how to change mass into moles. So if you want to pause the video and see, can I find the number of moles of sodium phosphide present? Go ahead and do that. And then when you're ready to check, unpause and we'll come back together. So let's do this together and we'll see if you've got it right. 3.4 grams times the molar mass of sodium phosphide which is 99.94 grams. And that will give us about 0.0340 moles. Since this is a three-step problem, try not to round your answers too much until the very end, but if you don't want to write down all 10 digits, if there's many of them, then that's fine. Then we're going to go on to step 2. Step 2 is our new one with our mole ratio. We want to find out the moles of magnesium phosphide. Let me just fix that because I'm writing the wrong symbols down there. Okay, so how many moles of magnesium phosphide do I have? Well, then I have to take my answer from part 1. We're down here trying to convert that number of moles of sodium phosphide to magnesium phosphide. So 0.0340 moles. And here I want to make sure I've got my units in here. And I'm going to multiply it by that ratio. So my ratio here, I've got 2 moles of magnesium phosphide from up in the balanced equation and 1 mole of magnesium phosphide. I'm going to put my moles of magnesium phosphide on the top. And on the bottom, I put my 2 moles of sodium phosphide on the bottom. So in my calculator, that means 0.0340 times 1 divided by 2, and I should get 0.0170 moles Mg3P2. And we look at our units, moles of sodium phosphide have canceled. So now we're over here trying to find out now what the mass of magnesium phosphide is. So if you want to try this step, go ahead and pause. We're going to take our answer here from step 2 and change it back to its mass. But this time you want the molar mass of magnesium phosphide, so you're going to have to do that calculation yourself. If you're ready to check, you can follow along with our answer here. So mass of magnesium phosphide, we take our moles from step 2 and we're going to multiply it by the molar mass. But this time we want the mass on the top because we want to end up with grams. So 134.87 grams per mole. When you get your answer, you should get about 2.292. And again, make sure you're rounding to significant digits. Here we want 2 significant digits, so it should be about 2.3. Okay, so there's a problem, full-on stoichiometry problem, where you're calculating the mass of one compound produced from the mass of another. So now we're going to do one more problem, and I'm going to help set it up, but then I want you to pause the video and try and see if you can do it more on your own. So here's the problem. Same balanced equation, I've already got that written out for you, and I've added in a part B, so we can just try an extension question for those of you interested. We'll come back to that in a minute. So in this question, it says you have 10.2 grams of sodium chloride produced. How many grams of sodium phosphide are required to react? This question's a little bit different. It's flipped around. Here you're given an amount for your product and it says, well, how much reactant would you need to get that amount? But it doesn't change anything for what we're doing. So let's write down what we have and then we'll write out the steps and I'm going to let you try. So here we have a mass of 10.2 grams of sodium chloride, and we need to find out how many grams of sodium phosphide were needed to produce that amount. Mass of one compound to the mass of another compound. Anytime you have 2 different masses of 2 different compounds, you have to think, I need a mole ratio which means I need to solve a stoichiometry problem. And if you have two compounds and they're not in moles, you've got to change them into moles to get started. So the steps you're going to do, step 1, change the mass of your product, sodium chloride, into moles using your molar mass of sodium chloride. Once you've got that, your second step is your mole ratio. That one you need to find your moles of sodium phosphide. This time the mole ratio will just be between these compounds. 2 moles of sodium phosphide, 6 moles sodium chloride. Once you have the moles of your reactant, then you're on to step 3. Change the moles into mass. Guess what? You're using molar mass again. So, what I want you to do is try and pause the video and see if you can do these 3 steps on your own. And when you're ready, come on back and we'll check the answer together. All right, so if you're ready to check, let's take a look. Here are your first 2 steps. So here we've got 10.2 grams of sodium chloride. We're going to change it into moles by dividing by the molar mass. And you should get somewhere around 0.1745 moles. That's step 1. So step 1 we've landed over here. Now we need to go on to step 2. This is the mole ratio, the new part. We need our ratio. We're starting off with sodium chloride. Moles of sodium chloride have to go in the denominator so they cancel. So take your moles, times it by your molar amount of sodium phosphide, which is 2 moles, and divide it by 6 moles of sodium chloride, and you should get about 0.0582. Then the last step, once you're at moles, you need to change this moles back to mass. So to do that, very last step, you want to take your moles, 0.0582, and multiply them by the molar mass of sodium phosphide, 99.94, and you should get around 5.816. Here we want 3 significant digits for our answer, so that answer should round to 5.82 grams. So there are other types of problems that involve stoichiometry that might not just involve mass. What if they throw in particles? So an extra add-on question for our lesson is, well, how many formula units would there be of sodium phosphide produced? What if that was the question? If that was the question, you would still end up doing a few of the steps the same. So step 1 would still have to be finding the moles of sodium chloride. That would not change. So we already have that calculation done here. Then we would need to change moles of our sodium chloride into moles of sodium phosphide. That doesn't change because we still need to get to that same compound. So step 2 would be exactly the same. Do your mole ratio. But step 3 here is where it changes. Instead of finding mass, guess what you're going to do? You're going to find particles of sodium phosphide. How do we go between moles and particles? Yep, that's right. Avogadro's number comes back in. So the process would be the same for the first 2 steps, but the last step, instead of changing to mass, you would change to particles. So step 1 and step 2 are the same. We're going to take our answer from step 2, and we are going to find the number of particles instead. So how would we do that? For part B, we want to find the particles for sodium phosphide. So we take our number of moles of sodium phosphide, and we use Avogadro's number, 6.02 times 10 to the 23 particles per mole. But since we've got sodium phosphide, which is formula units, we're going to use formula units. Our 1 mole is going to go on the bottom, and our 6.02 times 10 to the 23 formula units on the top. So if we do this and plug it in our calculator, you can give it a try. 0.0582 moles times 6.02 times 10 to the 23. And what do you get? You get about 3.503 times 10 to the 22 formula units. And when we look at that, again, 3 significant digits for this question, we get about 3.50 times 10 to the 22 formula units. So there's a few other little twists that can get thrown in with stoichiometry. A lot of the ones that you'll run into will be between moles and mass, but sometimes the ones to get you thinking a little bit harder are ones involving Avogadro's number.